Okay, so far we have been looking at this Radon transform, and we started analyzing a method for inverting the Radon transform, and we established something called the Fourier slice theorem. I will just backtrack a little bit and recap to make sure that we are all on the same page, so that our discussion today will carry on from where we left off in the last session. So, just to recollect the inverse Radon transform, the Radon transform itself, as you can see here on the screen, is given by this integral of this function, and remember the function f of x y is what we want to find. This is your mu in the Beer-Lambert law. We discussed this at the very beginning when we introduced this idea of tomography. So, f of x y, you can think of that as like a density, for example, right, and our aim is to get these projections and then invert these projections p theta of t, that are a function of two variables theta and t, and then get the actual density function f of x y. To do this, we made note of the fact that there is a excuse me, there is a coordinate transformation that relates the t and s coordinates, t being along the direction of the detector and s being along the direction of the ray. They are both perpendicular to each other if you have a parallel beam of incoming rays, and the ts are related to the xy coordinates of the object by a simple rotation matrix, right, like we have written down here. And this is just another way, this particular relation for t is just another way to look at the equation of one particular line, x cos theta plus y theta equal to t, t being the offset from the center, right. So, we said that if you take as 1D Fourier transform of p, that is shown over here, then you get this function called s theta of w. W is a spatial frequency because now t is getting removed, t is like a spatial variable in this axis, and this s theta of w is a 1D Fourier transform of p theta of t, and the s theta of w we said was related to the Fourier transform 2D Fourier transform of f of x y, right. And we worked out this relation precisely. So, for instance, if you take the expression for s theta of w, you will see that there is this integral, basically the Fourier integral in the 1D t variable, and then p theta itself is of course also an integral, right. And so, we use this to work out in the general case what we would need to relate s theta of w to f of u comma v, right. And we found that by doing some simple manipulation, we basically got this expression in the box, which we call the Fourier slice theorem, and this relates the Fourier transform of the 1D projection to the 2D Fourier transform in polar coordinates, right. And we looked at this in the frequency domain. If you take a single value p theta of t, you take its 1D Fourier transform, you are basically going to get one sliver along this line, a particular line at an angle theta in the Fourier space, right. And you can imagine doing this at various different angles. So, you take different projections and then you look at them, stack them up one by one, you are stacking them radially in 2D space, and the hope is that if you have enough theta slices, then you have enough information to cover the entire 2D plane, 2D frequency plane, UV plane, and once you have that, you can then use the inverse 2D inverse Fourier transform to completely recover the original function small f of x comma y. So, we said that the 2D situation was like this, and I showed you a sequence of images also where you have the sinogram. This is generated by taking, so each row in this image, for example, if you look at the intensity of that image, then in each row the image intensity corresponds to p theta of t, right. So, you take one of them, you take a 1D transform and then you stack it up, and then you will get this, you get the 2D field, right. We also made a brief mention about how you would do a 3D reconstruction. We will talk a little bit more about this perhaps in the next session, but then the idea is simple. You have the same configuration, but now it is only done layer by layer. So, every single stack is lined up, and you do the same thing for every stack. You have a huge parallel beam coming from here, that is the assumption. Of course, in practice it never works like that. You have a point source, and so we will talk about how to deal with point sources a little later on. But in principle, if you had something like this, you can then reconstruct stack by stack. For each stack you have a p theta, theta being the rotation about the vertical axis for the object. Okay. So, that will give you the set of stacks and you will get a full 3D field in principle again theoretically. So, today we will look at a slightly different interpretation of the scheme we developed, the Fourier slice theorem, and this is called the filtered back projection algorithm. It is an interesting algorithm because it tells you just by looking at the expression from the Fourier slice theorem in a slightly different point of view, you can actually get a completely different interpretation and use that for an actual efficient implementation. Now, in the interest of time we will not be able to go through an implementation from start to finish like we did for the case with DIC for example, but nonetheless this discussion of the filtered back projection should give you an idea of how to get started. Okay. So, let us say if you recall the 2D Fourier transform of or 2D inverse Fourier transform of a function, let me write down. So, you have a function f of x y and then you do a Fourier transform, you will get capital F of x y of u v, and to get the inverse transform, this is the forward transform, and to get the inverse transform you do the IFT, you will get f of x y, right. Now, let us start by writing down an expression for the inverse transform. If you recall, you have something goes minus infinity plus infinity minus infinity plus infinity f of u comma v exponential 2 pi I x u plus y v times du dv, right. For the Fourier transform you are integrating over x and y, now you are integrating over u and v. So, we now manipulate this expression and then use the Fourier slice theorem to come up with a more signal processing heavy interpretation of the exact same expression, okay, like I mentioned. So, let us start by converting this to polar coordinates. So, you basically convert u comma v to w comma theta just like we had before. W is like a radial coordinate and theta is like an angular coordinate, but this is in frequency space. So, your u will be w cos theta and v will be w sin theta. So, f of x comma y will be integral from 0 to 2 pi for the theta variable, integral 0 to infinity for the w variable, f of w cos theta comma w sin theta exponential 2 pi I x w cos theta plus y w sin theta, okay. And du dv, if you convert to polar coordinates, will give you w dw d theta, right, like r d r d theta, only now in the frequency domain. Okay, so, this is nothing fancy so far, we have only written down the inverse Fourier transform in polar coordinates. Let me just now maybe I will just use this. So, just use this instead of rewriting it again. Let me just split this into two parts, right. So, I have 0 to pi, 0 to infinity of this entire thing dw d theta, this entire thing with the w inside, right, plus integral pi to 2 pi integral 0 to infinity this entire thing again dw d theta, okay. I am only splitting the integral. So, this is easier to rewrite because I am not writing the full expression. So, you have integral 0 to pi integral 0 to infinity the entire thing dw d theta plus integral pi to 2 pi 0 to infinity dw d theta, okay. Now, in the second integral I can change variables. So, I change pi plus theta to theta, okay. So, pi plus theta I am going to call theta, right, which means I have to subtract pi from the actual theta that is in the integral. So, the second integral if I do this will be 0 to pi 0 to infinity, everything else will remain unchanged, but you will get f of theta plus pi comma w, right. This is the same as f of w cos theta plus pi and so on, right. Okay. Now, there is a property of the 2D Fourier transform that this is equal to f of minus w comma theta. Okay, this is a property of the Fourier transform. Which basically says if you go in the frequency domain and you take some, you use w as an angle as a directional variable. So, w in this direction is positive, w in this direction is negative. Then w at theta and w at pi plus theta can be related, f at this particular point, for example f at this point is the same as f of minus w at theta. Okay, that is what this says. This is u, this is v. Okay. So, if you do that, then this integral gets converted to 0 to pi integral 0 to infinity f of minus w comma theta blah 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 with all the exponential stuff, that is all here. I have not written that down in the previous integral too. You will have w dw d theta. Okay. Now, in this I will change w to minus w, change of variable. If you do that, you will get a minus w here, you will get a minus dw here, and you will get a plus w here, and your limits will go from minus infinity to 0. Okay. So, if you do that and you combine that with the first integral, you can basically write f of x comma y is integral 0 to pi integral minus infinity to plus infinity of this entire thing, which I am going to write down now, which is f of w cos theta w sin theta exponential 2 pi I w x cos theta plus y sin theta w dw d theta. Okay, just some simple manipulation, nothing very fancy, right, and it is just still the expression for the inverse transform. Okay. Now, remember the equation for a line was x cos theta plus y sin theta equal to t. Okay, that was the equation for the line that we used at the start, right. So, this fellow inside is exponential of 2 pi I w t. Okay. And remember from the Fourier slice theorem, this guy was s theta of w, right. This was the 1D transform of the single projection. Okay. Remember, if you go back, we had this, right, this is the Fourier slice theorem, this was s theta of w, right. So, now if you put this stuff together, you will get f of x comma y is equal to integral 0 to pi integral minus infinity to plus infinity s theta of w times w with a magnitude exponential 2 pi I w t dw d theta. Okay. This is a function of t, because w is going to be integrated out, the only remaining variable is t. So, we will call this function q theta of t. Okay. If you did not have this mod w sitting in the middle, then this is basically just p theta of t, because it will be the inverse 1D Fourier transform of s. Remember, p theta of t, if you do a Fourier transform you get s theta of w. So, if you do an inverse transform of s theta of w, you should get p theta of t, right. So, if the w was not here, this mod magnitude w excuse me, then you will only have p theta of t, but now you have a different function which I am calling q theta of t, and this q theta of t is a filtered version of p theta of t. Okay. There is a property of Fourier transforms which we have not really touched on here, which is that if you have a convolution integral, again I am just going to mention it, it might not be as critical now because it needs a little bit of discussion. If you have a convolution of two functions in real space, then in the Fourier space a convolution becomes a product, right. So, this is like a filter that is being applied to this before you take the inverse transform. Okay. This filter is called a ramp filter because it is proportional to the frequency. So, you basically take S theta of w, you take a filtered inverse transform and you will get q theta of t, the function. Okay. So, you can do this filtering very easily in the Fourier domain. Now, once you have q theta of t for a particular theta, you can get f of x y, and for a particular t of course, you can get f x y by just integrating over all theta. So, now you have 0 to pi q theta of, remember what t was x cos theta plus y sin theta d theta, right. So, for every single theta you just add up the contributions from q naught at any particular x and y and you will get the actual function. Now, this is a much better implementation, much better way of implementing this entire scheme as opposed to just naively taking slices, taking 1D transforms and then taking the inverse 2D Fourier transform like we discussed with the Fourier slice theorem, and the reason is because it has a nice geometric interpretation. Okay. So, we will look at that now. So, what do we have? We have q theta of t is this fellow, and we have f of x y is 0 to pi q theta of t. Let me write this explicitly, right, x cos theta plus y sin theta d theta. Okay. So, let us look at what these two expressions are telling us geometrically. So, here is our f of x y, we have some unknown function and we take a projection, let us say this is our projection. So, our rays are coming like this. Okay, let me erase this, we know what f of x y is, I will need some space to draw this carefully. Okay. And now you have this guy. So, you have a p theta, this is your p theta of t, this is your t variable of course. Then you take a Fourier transform of this, you will get an s theta of w, then you do a filtered inverse transform of that, you will get a q theta of t, this is q theta of t. Okay, it is a filtered version of p theta of t. Now, at a particular t location, remember this is all at a particular theta, right. So, this is your normal and this is your theta, right. We define theta with respect to the normal. So, we will use the same convention. Assume that these two lines are parallel, right. I have tried to indicate that. Okay. Now, at this particular theta, this single projection, this single q theta at a particular location t. So, let us take this location t, right. So, our origin is here, let us say. So, t is measured from here. So, this value let us say at some t naught at this point, you have a value of the function q, right, that has some value, right. Now, you take that value and assign it to this entire line. okay. Initially you initially do not know anything about f of x y, everything is 0, let us say. This is the first projection you are starting with. You go back and you assign this to every single point along this line, okay. Now if you have another projection, let us say like this, you have another p like this whatever, and you have another q, let us say this is your q theta 2 of t, p theta 2 of t, let us say. Now you go back for some value of again t equal to 0 is here, this is the origin. So t is measured from here. Now for this value of t, you go back for this entire slice, you update the value of f at this slice as the value that it had before plus the value of this q. Go back to this point, value it had plus the value of q, this point value it had value. So initially if this is all 0, you have only updated this blue line first. When you come here, you take this value of q theta of t and you update that by adding to it this value of q theta 2 of t. So one point now has become a little bit more focused than the others, which is the point of intersection of these two. Likewise if you go to some other t, let us say you go to this t, well this t is outside, let us take this t, then this point which had this value has now been more refined. Likewise this point which had a value coming from this q theta now is more refined because it has a value coming from this q theta. So this process is called back projection. So you are projecting back the q thetas into the actual spatial domain, one projection at a time, okay. So you have a filtering step, this is called a filtering step like we discussed, and this is called a back projection step. Okay. Now you can easily imagine setting this up. If you have a 2D array, again in the interest of time we will not be able to do this for you, but I think this should give you enough information to get started, right. So let us say you have a 2D array and you want to reconstruct the value of f of x y on this 2D array, okay. So at each location, each pixel location, you can back project this value of the line that is passing through this pixel location on this projection at this theta. To that you add up the projection coming from this theta, and to that you add up the projection coming from another theta, and so on, you keep going till you cover all the projections, and finally you will have the value of f of x y at that point, okay. So this is a very clean way of implementing this reconstruction scheme, right, as opposed to doing an inverse Fourier transform where you only have radial slices at periodic intervals. The other problem with doing an inverse Fourier transform, I will just mention that now, is remember we said that if this is your UV domain, then every time you take an s theta of w, you are looking at one radial slice, right. So you have one radial slice here, you have one radial slice here, one like this and so on. Now the problem is you have data along this slice, but the further you go from the origin, you will start seeing gaps in the data, right, because obviously here this data point and this data point are next to each other, this and this, but this data point, if these are the only projections you have, this data point and this data point have a lot of missing information in the middle. So you have to do some interpolation. If you do the filtering back projection, you are not you do not have this issue, right. So this issue becomes amplified because you have to do filtering for these points, you have to do interpolation for these points. If you did the naive 2D Fourier slice business, you have to do interpolation for everything in between. That is a problem everywhere, right. So you have to do more interpolation at larger distances from the origin, which really does not make sense because you have a parallel beam, you can't have a dependence on the radial distance, right, because the parallel beam is seemingly sampling everything equally. So you can't have this loss of data as you go further away, right. So the interpolation leads to results from data loss. So you will have artifacts when you do the inverse 2D inverse Fourier transform, because the data is not dense. Okay, so that is a basic problem with just directly implementing the Fourier slice theorem, but now with the filtered back projection scheme you should not have this issue. Okay. So, I will just outline a sequence of steps, so that if you want to implement your own scheme it should be fairly simple to do. So, first step, so here let me summarize. So, sequence of steps. For FBP stands for filtered back projection. Okay. Okay, the first step is you obtain of course p theta of t for all values of theta and t, okay, whatever within some domain you have discretized it, it is obtained at some angle, you know, at some angular some discretized angular distribution, right. So, you have some delta theta and delta theta you have, and so you have those many slices. The second is for each of them you compute S theta of w, take the 1D Fourier transform, which is easy enough to do because you are not messing with the slices, you are messing only with the t dependence. Now you then do the filtering step. So, you take S theta of w and then you compute q theta of t again. So, you are now filtering the data, okay. And remember what the ramp is doing, the ramp is sort of weighting these distributions back, because the further you are the larger weight you assign to the further you are from the origin the larger weight is assigned to that particular data point, and so it is actually filtering and giving you a new filtered value q theta of t, which presumably does not have this artifact of data loss for larger radial distances in the frequency plane. Once you get q theta of t you do the back projection, and the back projection is done for all values of theta, okay. And notice one more subtle thing, it just perhaps slipped under the radar a little bit. We had this discussion about having the integral go only from 0 to pi, right, because if you have one ray and you rotate the ray by 180 degrees you are going to get the same information. So, this automatically is taken care of in our limit for the integral. So, you only have to do, when you do the discretization you only have to do 0 to pi, because you have a parallel beam. Of course, if you have a fan beam the situation is slightly different, and so you back project for all of the theta projections you have, and when you do the back projection you update at some ith pixel location, you update the value with q theta from corresponding, you know, whatever theta j of xi cos theta j, this is your t, right. So, you update it with this, which means you add this value to what you already have and you sum over all theta j's, okay. So, for every single projection you go back, add it, and then you get it, and then at the end of the step you have your f of x y in an array, right. Now, you can imagine, like we discussed for the 3D case, you can imagine doing the same thing. You can start with a single slice, do this entire operation for a single slice and then move to the next slice and then keep going from there, okay. So, that basically covers how one would go about implementing a filtered back projection scheme. What we will do next in the next session is to look at more realistic imaging configuration. We will talk about what is called a fan beam projection, and then I will discuss briefly this idea about a cone beam projection and what is called the Feldkamp algorithm, and based on that you should be able to appreciate how actual practical implementations are done with more realistic sources, and with that we will wrap up our discussion about optical tomography.